Okay, so we're going to be moving on to lesson 4, talking about electric field. Okay, what is an electric field? Okay, read the definition. The region in which a force is exerted on an electric charge. So it's done by Michael Faraday. I don't know if you've heard of his name. He also helped develop a lot of different principles, like the Motors principle and stuff. So he's the one who developed the idea of an electric field. So basically, an electric field is represented by a force vector. And we show the direction and magnitude of the electric force of a small positive test charge. Okay, let's read this again. A field shows direction and magnitude of the electric force on a small positive test charge. Okay, big word. I need you to remember the test charge is positive. Okay, so keep that in mind. It will make sense later on. Here is the equation of what electric field is, and the unit for electric field is Newton per coulombs. I think you can make that out from here. Force is measured in Newton. We know that a charge is measured in coulombs. And just to help you recall, okay, we're just going to do a little comparison with gravity and electrical. Okay, you have learned that Fg is gm over r squared. You have learned the electric force is kq1q2 over r squared. Do you remember the equation Fg equals to mg? Okay. Do you also remember what we call this lowercase g? What's the name? If I say right now, what do we call g? We used to call it acceleration due to gravity, but we also call that this is gravitational field strength. I don't know if you remember that. Gravitational field strength. Okay. Now, let's take a look at the new equation today. Okay, new equation today. If I rearrange this equation, do you see how this is Q epsilon? I just put the Q on the other side. Okay, let's put it in the comparison. Fe is equals to Q epsilon. This is called the electric field. Okay. Gravitational field is measured in Newton per kilogram. Electrical field is measured in Newton in coulombs. Do you see the similarity? So really, what we could have done is how we found it is basically put these two equations together and put these two equations together. That's why we can say to find the field, remember how we can put the two equations, Fg equals to Fg, and I know that is m times g is equals to gmm over r squared. That's why we came up with the new equation. The m and m cancel. Small g, the gravitational field is this. And if I do the exact same thing between the Fe and the Fe, Fe equals Fe. The other way to find out what epsilon, this is called epsilon, the electric field, the symbol is epsilon. Q epsilon is equals to K Q1 Q2 over R squared. This Q being one of the Q. Epsilon is also K Q, whatever that charge of the object is square. The only thing that's different between gravity and electric, well, there's a couple other things too. Okay, like if you remember the pointers, okay, gravitational force and field are really, really small. Okay, electric is slightly larger. But then the other thing is gravitational are always only attractive, right? They can only point one direction, okay? But then this one could be attractive or repulsive, depending, right? So the similarity and difference, you have to be careful, okay? So let's keep going. All right, how do you draw a force field? Okay, you need to know how to draw electrical force field, okay? Force field, electrical force field always goes from positive towards the negative, okay? I don't know if you understand that, but this picture really is the Earth force field. It's the same as the Earth force field. Like whenever I have something that have a mass, object will start accelerating towards it, okay? That's the exact same picture with the Earth, okay? And that's the force field. Okay, so you need to, number one, if this is called the point charge, these are called the point charge. So I have one single point. Okay, point charge can be positive or negative, and they can interact with each other. If I change the point charge, and if I put two together, they can start repelling. These two are repelling, positive and positive, and that's why the forces, see how it's still leaving from the positive going to the other direction? Okay, same thing, this is repulsive again. Okay, and this is now attractive. Okay, so I have a plus and a minus. Okay, and it's attractive, and the rule stays the same. It goes from positive towards the negative. And they're showing you that if you have electric eel or something, some animals and fish, they produce their own electrical field around them. All right, so this is what I tried to demonstrate with you just now. Okay, if there is a positive point charge, a positively charged sphere that is small enough to be considered a point charge, it produces a field. And then that field, at any point distant r from the sphere, to work out how strong the field is, this is the equation. Okay? And how did we get that? It's basically from just equating the two equations that I did. Okay? So this thing on the right-hand side is what I used to explain how to get the equation. So there's two new equations today, right? Fe equals Q epsilon, the Coulomb's law you learned yesterday, and then now you have basically a new one that joins the two together. So two equations so far. Okay, but I hope the similarity can make it easier for you to understand by just kind of tying with the gravitational. Okay, where Q1 is on the spheres. Okay, an electric field of a negatively charged is identical except pointing inwards. So they're basically saying how strong the field is the same depending on plus or minus. It all depends on the magnitude of the charge. Like it matters for the magnitude of the charge, but being positive or negative will not make it stronger or weaker. It just points to a different direction. Okay, when you do these questions, similar to the forces question that we've been doing from Coulomb's law, we do not include the sign of the charge in the calculation. We determine the direction from a diagram. I'm going to specify this. You're going to use a vector diagram to solve for the vector net, like the net force. Okay, we've talked about point charges. We're now moving on to, there also could be electric field with a parallel plate. Okay, and these type, we call it the uniform electric field. Consider two parallel plate that carries equal but opposite charge. So in this picture, positive is at the top and negative is at the bottom. And so it's causing a field. If there is a separation between the plate that is very small in comparison to the surface area, we would say that it remains uniform. If the positive is at the top and the negative is at the bottom, you will have a net force acting straight down. So what that means is if I actually have a little piece of particle, okay, and if there is the acceleration is coming this way, okay, the reason why there's an acceleration going this way is if I put a positive particle, do you see how it's going to be repelling from the top but attracting to the bottom? It's going to cause a net force. We call it the net electric force that is causing it to accelerate downwards. All right, example number 1. What is the electric field 0.6 meters away from a small sphere with a positively charge of 1.2 times 10 to the negative 8? So they're asking for what is the electric field. So first of all, recognize what electric field means, right? The epsilon symbol. And they would like you to find out, they tell you that the distance away is 0.60 meters. And this charge is 1.2 times 10 to the negative 8 coulombs. So look for the equation that helps you calculate the epsilon. So that would be this one, right? I got Q1 and R squared. Hopefully you remember your K is a constant. Okay, so I know that epsilon is K Q over R squared. So K is 8.99 times 10 to the 9 times the Q, which is 1.2 times 10 to the negative 8 coulombs, all divided by the radius square. So take out your calculator, punch this in. And you know how these are numbers that I probably would punch it in 2 times to make sure I'm getting the right answer. Okay, so 2 significant digit is what I need. So I got 299.6666667. So I need 2 sig dig, so I have to round it to 300, but 300 doesn't work, so you're going to have to put it in 3.0 times 10 to the 2. Unit for epsilon is Newton per coulombs. Question 2. 2 charges. One is 3.2 times 10 to the negative 9 coulombs. The other is negative 6.4 times 10 to the negative 9, and they are 42 centimeters apart. Calculate the net electric field at point P, 15 centimeters from the positive charge, on the line connecting the charges. Let's draw a little bit distance here. Okay, so I know that between first charge, the positive charge, and point P is 15 centimeters, and I'm going to put it in meters. And they tell you that between the 2 charges, the whole distance is 0.42 meters. So that means between P and the negative charge is 0.42 minus 0.15. So this is 0.27 meters. Okay, so I'm just getting the distance ready. Okay, so let's study this together. We have a positive charge. I'm going to call this charge 1. And we have a negative charge that is over here. We're going to call this point 2. And you have a point P. Okay, I need you to remember, I told you to pay attention to it right from the beginning. This is called the test charge, okay? We actually consider this to be the test charge. You do need to know what charge this is to know that if it's attracting and repelling. Unlike gravity, right? I need to know if it's positive or negative, okay? First thing to remember how I said electric field line always goes from positive to negative, okay? You're trying to calculate how strong the field is. Your ultimate answer should be going towards the right? Because it's going positive to negative. My overall answer should be right. What charge do you think P has to be to make it to the right? It wants to attract and repel, right? Because I have one side is positive, one side is negative. All right, so that's higher order thinking. If you have no idea what I'm talking about, I need you to go back to the right at the beginning. I need you to take a look at this line again. Basically, the field is when we assume the electric force that is acting on a small positive test charge. So meaning, every time when you do electric field question, you need to make an assumption that this charge is a plus. Even though nowhere in the question it will tell you, it will only tell you this at point P. We assume that there's a test charge, and we assume that it's a plus. This is probably something that people might get confused on the test. Is like, well, how am I supposed to know if it's positive or negative? It's positive. When you ask that question and roll your eyes at me, it's positive, okay? We assume point charge to be positive, okay? All right, so now let's work out the little vectors here, okay? Similar to the same question that you were doing yesterday when we're doing Coulomb's law, finding out the net force, you're going to have to separately calculate force from 1 and force from 2. But this time, instead of force, I'm finding the field, okay? So I'm looking for field, okay, between charge 1 and this point, okay? This point is positive, positive and positive repel. So that means the force field, electric field from 1 is going to be going towards the right-hand side. Now consider this point to now the negative. Okay, negative on the right hand side, I have positive in the middle. Positive and negative, they attract, meaning I need to calculate the epsilon, the field that is caused by charge negative, which is the second charge. And then you just go ahead and use the same equation and calculate it twice. So separately, you would calculate the force. So I'm going to calculate epsilon 1, okay? The first field is KQ1 over R. I'm going to call it R1 square, okay? This is R1, the distance between the charge and the point, okay? And then you're going to repeat the same question, and you're going to find epsilon 2, KQ2 now, based on the second charge, over the second radius, which is R2, which is the distance between the point charge and the negative. Okay, so see the way I set it up? Keep it organized, right? And remember, we don't plug in the negatives in the question. These are vector questions. We deal with the vectors by adding the vectors together later on. Okay, so finishing this up, so 8.99 times 10 to the 9 times Q1, which is 3.2, 10 to the negative 9, divided by R1, which is 0.15. 8.99 E9 times 3.2 E negative 9 divided by 0.15 square. So I got the answer for the first one to be 1278.5. I know, I don't like to round. Okay, newtons per coulomb. This is to the right based on the picture. Okay, repeat the question for number 2, epsilon 2. I'm just going to do it down here. So 8.99 times 10 to the 9 times Q2, second charge was bigger. Okay, but it's further away. Okay, so I make sure I use charge for number 2. So 8.99 to the 9 times 6.4 to the negative 9 divided by 0.27 square. 789.2455418 Newton per coulomb to the right. Okay, so what is the overall net? Epsilon. Both are going to the right. To find the net electric field, I just have to add the two together. I'm just not writing all the number down, but I'll still punch it all in together. Okay, so I got all together with two significant digits, 2.1 times 10 to the 3 newtons per coulombs to the right. Okay, make sure you have your direction here. Sig digs. All right. Okay, so I already explained the point charge. Remember I said you have to learn how to draw the point charge and the field. So from between a positive and a negative field, it goes from positive to negative. So it makes sense that if I'm looking at this area right here, that my field should be going to the right. All right, so let's look at this picture now. Okay, how about if I have charge like that and they would like to, okay, so let's read this together. 2 point charges are arranged as shown. Q1 is 4 to the negative 6. Q2 is negative 2. So I'm just going to write this down. I know this is positive and I know this is minus. And the radius from the picture is 3 centimeters. They want you to calculate. So both of the R's are 3. And they want you to calculate the magnitude of the electric field in the origin, which is right here. Okay, so this is your point P. Okay, remember we assume point P to be positive. Okay, so that means point P is going to feel the electric field from Q1 and Q2. And so we're going to separately do the math together. Okay, between Q1 and the P, positive and positive, they repel. So at point P, it is going to have an epsilon that is going down. I'm going to call this epsilon 1. Okay? And then between point P and Q2, one is plus, one is minus. They are attracting. So when they're attracting, it's going to be pulling towards the right. And this is epsilon 2. Okay, so I'm going to do the calculation for epsilon 1 and 2. And then I have to find the net force by adding the red and the blue vectors together, just like lesson 1 and lesson 2, just adding vectors. Okay, so let's do the first one. Epsilon 1 is K, use the charge for Q1, and the distance between them, I think they're the same, square. So K, 8.99 times 10 to the 9. Q1 from the question is 4 times 10 to the negative 6. Distance between point P and Q1 is R. In the question, they told you that it is 3 centimeters, so I'm just going to turn it into 0.03 meters divided by 100. So 8.99 times 4e negative 6. Okay, humongous number. 399,555. Okay, I got that, and it's going downwards. I'm just going to call it down and right. You can call it north and south, whatever. It didn't say, so you can call it whatever. Okay, so I'm going to work on the second one. Second one is epsilon 2. So I need to find what is the field from charge 2 at the point P. So KQ2 over R squared. The R's are the same, so I'm not going to specify 1 or 2. Okay, don't put in your your negative, right? We don't put the negative in when we do the field. Over R. R is the same R. Okay, and this is going to the right. Okay, so I got two epsilon, two vectors. We're not talking about forces, but we're talking about the field. But they're vectors, one that's going down and one that's going to the right, and I need to find the net field. So that means I need to do a vector diagram and figure out what is the overall. So I'm going to have this 399, I'm not writing all the number out for now. And then it's going to go down, and then it's going to go towards the right at 199. And so the overall epsilon net will be this one. So E net, epsilon net, and it's a right angle triangle, so I'm going to use the Pythagorean theorem. And because this is a vector, I need to find the angle. All right, so epsilon net, Pythagorean. Okay, software, E net. Take the root. So the answer I got is 4.7. No. 4.5 times 10 to the 7. Two significant digits. Unit is Newton per coulombs. And to figure out the angle, I use tangent, opposite, divided by the adjacent. It's 27. So that means the direction of the field is down 27 to the right. Okay, does it make sense that the direction of a field for this picture to be going to kind of down to the right? Yes or no? Yes or no? All right, let's draw a picture together. Okay, you need to know how to draw the force field, right? So if they have a plus and they have a minus, and they're like, hey, can you draw me the electric field lines? Okay, it's like I took this picture right here, and I just I rotate it, right? Like I rotate it so that they're not exactly horizontal to each other. I kind of rotate it a little bit, but the rule stays the same. The field line goes from positive to negative, right? So my field line would be something like this. Okay, it could be thicker. Okay, so the field line goes like this, positive to negative. Okay, do you see this field line? I know they're not the best thing, but let's just finish drawing the field line just because we're having fun here. They all go into the negative, out from the positive. Okay, so which point are we talking about? Let's go back to the picture. I want to know the point that is at the bottom left, right? So I need to know what direction of the vector right here. Like if I drop a line here and if I drop a line here, I want to know what is the force vector. Okay, does it make sense that this force vector is kind of slightly going this way, which is what we have in the black, right? Like right here, right? Bottom to the down, 27 to the right. Okay, and that's what it means. That's what you calculated. This is the black line that we calculated. This is the epsilon net that we calculated from the picture.